Now I'm going to talk about a special trick from the theory of differential equations. It's a very nice little thing, right? So first of all, recall the definition of linear dependence. And so two functions defined on an interval are said to be linearly independent. Right? So if this equation holds only when both coefficients are 0. Right? So in other words, if you have a linear combination and it is 0 for all values of t, then the only way it can be done if it is a trivial linear combination, the coefficients are 0. Right, so a little question for online discussion is just for you to review linear algebra. Alright, here is an example. Of course, so these two functions are linearly dependent. But these two functions, t and t square and 5t square are linearly dependent, but t and t square are linearly independent. Well, and here is the trick. So let us introduce it to this definition. So the Wronskian of two functions is a certain determinant, right? So if you take two functions, so then you construct a matrix where the first row is the two functions and the second row is the derivatives of the two functions, and then you compute its determinant. So let me emphasize that the Wronskian of two functions is again a function of t. Right? So here is, for example, how we can compute the Wronskian of sine t and cosine t. But if you want to, I don't know, say Wronskian of two random functions, so Wronskian of, say, I don't know, ln t and minus t square, it is doable, so it is going to be a function of t. So then we should write the determinant of this matrix, ln t minus t square. So then the derivative is 1 over t, and the derivative of minus t square is minus 2t. And then we can compute the determinant, so it's going to be minus 2t ln t, minus plus t squared times 1 over t is t. So that's the 2t ln t plus t. So that's the Wronskian too. And here is a theorem. So if f and g are two differentiable functions, and there is a point at which the Wronskian is not 0, then these two functions are linearly independent. So that's how you can check that the functions are linearly independent. And the proof is very simple. So if you want to prove it, if at some point the Wronskian is not 0, then the functions are linearly independent, that what we need to do is to show that if the functions are linearly dependent, then the Wronskian is going to be 0 at all points. Right? So if they were linearly dependent, then it means that one of them is a constant multiple of the other. Then we calculate the Wronskian, and then we see that it is indeed 0. Well, so in other words, for arbitrary functions, what we know is that if at some point the Wronskian is not 0, then the functions are linearly independent. But is it true that if the Wronskian is 0 everywhere, then the functions are linearly dependent? So the answer is no, and here is a counterexample. Right? So here it is straightforward to check that the Wronskian is 0 for all t, but to verify that these functions are linearly independent may be a bit tricky. You can try to do it yourself, or you can read the textbook. It is explicitly explained in the textbook. But anyway, here is the example of two functions such that the Wronskian is 0, but the functions are linearly independent. So my next point is to show that this may happen for arbitrary functions, but this never happens for solutions of a second-order differential equation. So in other words, if our functions are solutions of a second-order differential equation, then either they are linearly dependent, and then the Wronskian is 0, or they are linearly independent, and then the Wronskian is not 0.